Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. Last time, I think the last topic was we were talking about arc consistency. I'll remind you quickly with the context. We were talking about solving CSPs. We're talking about backtracking search, and within backtracking search, we said that there are three improvements over the standard backtracking search or the core backtracking search algorithm, which are filtering, ordering, and structure. Within filtering, we discussed two ideas: forward checking, where we check whenever we assign a value, we check the arcs between that variable and the unassigned variables, and also discussed last time arc consistency, where we check all the arcs. We check the consistency of all the arcs, even the ones with between the unassigned variables. We saw example, I think, last time, or multiple examples. Today we'll start with the pseudocode, and then we will continue talking, inshallah, about we'll see a couple of demos, and inshallah we'll talk about ordering. The algorithm for arc consistency, if you remember, we have to check all the arcs. So initially we have a queue of the arcs that has all the arcs initially, and we go over the loop over the queue. We get one arc and we check its consistency. If we found that we removed any value from checking the consistency of that arc, as we discussed last time, we only delete from the tail, then we will have to put back all the arcs that are pointing to that tail, because they might be now inconsistent. They might become now inconsistent after we remove the values from the tail. So we have to add them back to the queue, and we continue working on the queue until the queue is empty. Now let's check what we do when we check the consistency. So that's this function. So in this function, we basically go through all the values in the tail, okay, and we check if there is any value that will be consistent with that value. If there's any value from the head that is consistent with that value in the tail. If we don't find any value that is consistent, then we'll have to delete that value from the tail. Okay, so we'll have to delete it, and we'll continue. And of course, we will have to indicate that we removed something, so that when we come back here, we'll have to add all the neighboring variables to the queue. So this is the main idea or main algorithm for arc consistency. Now this is checking arc consistency for all edges, and remember that we have to do that every time we assign a new value to a variable. So this is within the scope of the backtracking algorithm. So that's not the whole thing, of course, that's just the step of doing arc consistency. Now here we say that we detecting all possible future problems is NP hard. If you remember from your algorithms course, or I think data structures course, one of them, you know that there is a type of problems called NP hard, and one of them is the satisfiability problem. That's the satisfiability problem is the problem where you want to assign values to variables to satisfy a Boolean expression. You can reduce this problem to that, and thus this problem is actually NP hard. So any question about the algorithm, by the way, before we move on? Any questions? Yes, Saad? Yes. Yes. Yes, which is the tail. Yeah, no, checking all the values here with the Exactly, checking all the values here with all the values there, so that we can find for every value in the tail, we check all the values in the head to see if there is any that is consistent with it. Okay, is that clear now? Okay, any other questions? Okay, now let me show you a demo for arc consistency. Okay, let me first explain this. So this is the constraint graph, and don't worry about these rectangles. These are just names for the edges. Okay, but ignoring these rectangles, the rest is the constraint graph, and you will find a name for each row here. We are talking about 5 queens or n queens problem. So the rows are A, B, C, D, E, which are the variables. Remember that in a formulation we assign a value for each row, which means that which column in that row we will put the queen in. So initially the domains for every variables are all 1, 2, 3, 4, 5. Okay, and if we go now and check the consistency for all edges, initially we'll find all of the edges or all of the arcs consistent. Okay. So this is the demo on an applet. You will see that as we go, some of the edges will become green, which means that they are consistent. Some of them are blue, which means that they are now checked. Eventually, all of them will be green because initially everything is consistent. So the blue ones are are the ones in the queue. Now, after we are done, so now everything is green. Now let's assign a value to a variable. So we'll start with that variable. We'll assign a value to it. Let's say that we'll assign the value 1. Okay, so we'll assign the value 1 to that variable. Now when we assign the value 1 to that variable, you see that now it's just 1. And once we assign a value to a variable, we need to do arc consistency for the whole graph, for all arcs. Okay, so remember, what is the meaning of assigning 1 here? That means that we will have a queen here. We will have a queen here. Now, what do we expect to happen when we do arc consistency? The first thing that will be affected by putting a queen here, of course, actually it's the only one, will be the only one in the first stage, will be B. Because for B, we cannot, for example, put the queen here or here if we have a queen here. Okay, so if we check this arc from that side, it will be okay because there is a value that is consistent with 1. But if we check that arc from the other side, okay, now if we check the arc from in that direction, we cannot find the consistent value with 1 here, so we'll have to remove 1 here from here. We will also have to remove 2 from here because we cannot put a queen here or there. So after checking the consistency of that arc, you will find that 1 and 2 should disappear. So the queen is here, and now we are checking. Now it shrinks to 3, 4, 5 only. Okay, طيب. Now we should add to the queue the arcs that are pointing to that node. So we'll have to add this one, and this one, and this one. Okay, so this one, and this one, and this one, which is from here. So this will be in the queue, and we'll have to check them now in the queue. So if we run the rest of the arc consistency, it will, as you see, it will shrink the values here and other nodes also. So that shows you how arc consistency works. You can actually run this at your side. And by the way, there is audio for some of the videos. There is audio that explains what's going on, so you can run it at your side, inshallah. Now let me talk about the limitations of arc consistency. Will arc consistency find all possible problems? Of course, the answer is no. But let's check some of the examples. Let's look at this constraint graph. If we check arc consistency for all arcs, can we see any problem? Let's see this arc. Now we assign this to red. There's no problem in that direction because we can assign any of these two. Now from that direction, there's also no problem because for this green, we have red. For this blue, we also have red. There's no problem. So that arc is consistent from both directions. And if you check all the arcs here in all directions, you will find that they are consistent. Time. Can we have a solution for that problem? And do you see a solution to this? Yes, at that stage, there is no problems at all. All the arcs are consistent. But eventually, will we have a solution? The answer is yes. We can have a solution, of course, for this problem because we can assign here, of course, this is assigned already to red, but here we can assign green, we can assign blue here, or vice versa. Both are solutions to this problem. So there's no problem at all with this. There's no failure that arc consistency wouldn't detect. Now let's look at this constraint graph. If you check the arcs, all the arcs in all directions, again you will not find any inconsistency. All the arcs in all directions are consistent. For example, here for this red value, you can assign here blue if we are talking about this arc. For blue, we can assign red, and vice versa in all directions, in all arcs. So our consistency will find no problem with this graph. Now let's think about the solution of this graph or this CSP problem. Can we find a solution actually to this problem? If you look at this constraint graph, can we find a solution? Actually, no. There's no way that you find a solution here. If you assign red here, you will have to assign blue here, and then you will have no choice, no option here to assign. So there is no solution actually to this problem. There is a problem with this graph, but our consistency will not be able to detect that problem. Type. Now the question is why? Why our consistency didn't detect that problem? The answer is that our consistency so far checks only arcs between two variables. It checks pairs of variables. So if there is no problem with that pair, it will continue. And as you see here, there are no problems with any pairs of variables, but there is a problem with the three variables together, which is beyond the capabilities of arc consistency. So there will be a problem here, but arc consistency will not be able to find it. And remember again that arc consistency still runs inside the backtracking search. So in this case, if we are in a bigger graph, we'll have to backtrack and find a way around this problem. But it will not detect it early. Actually, it will not detect it at all. It has to fail at some point in the future. Do you have any questions before we see these demos? Questions? Yes, Saad? Yes, exactly. Yes. Yes. It depends whether we failed or not. If we couldn't, if at some point we couldn't make any of the arcs consistent by removing values, then we have to backtrack. Remember, all of this is within the backtrack search. So if we failed to make all the arcs consistent, then we have to go back and change something that we did before. Yes, you are right so far. We will generalize this next lecture, or if we have time today. But so far, yes, it is for binary. Yes. Okay, now let me show you a demo that will show you, I hope clearly, the difference between the performance of forward checking and the performance of arc consistency. So let's see this. So again, this complex map coloring problem. The domains are inside each of the nodes, which are the variables that we want to color. And here we are doing forward checking. So initially we'll assign a value to the first variable, which is blue here. Now once we assign blue, we have to remove blue from all the neighbors. So blue is gone from here, blue is gone from here. Then we assign a value for the next variable. Of course, we'll have to assign one of these two colors, and we'll assign red next. Okay, so now once we assign red here, look what happens here. We have to have only green, because we cannot have blue and red. So we have only one possible value here, which is green. But forward checking don't go beyond that. It only checks the variables that are linked to the just assigned variable. Now, what is the next variable that will be assigned? This one, and it has no problem. We'll start by assigning it blue. Now, once we assign this blue, blue is gone from here, gone from here, and gone from here also. Next is that variable. We'll assign it red. Okay, blue is gone, of course, so we'll assign it red. Now, once we assign that red, look what happens here. Now this one has only green. This one has only green. No problem for this, but if you look back to this one, it only has green. So that means that there is a problem here. So there is a failure here that will happen now or later. We'll have to backtrack at some point, because this cannot happen together. Both of these nodes cannot be green together. But forward checking will not detect it now. Why is that? Because forward checking doesn't check arcs between unassigned variables. Those are unassigned variables yet. So forward checking doesn't see them. So we'll continue with this one. Now we can assign, of course, blue to this one, because the order is blue, red, green. So we'll assign, as you will see now, sorry. Yes, so blue here, okay, and then we'll assign red here, because we cannot assign blue. Now the next one is this one, so we'll have to assign it blue. Okay, now we come to this one. This one has only one value, so it has to be assigned green. Once we assign this green is gone from here. That's not a problem, but also green is gone from here, which is now a problem. Now only forward checking will detect a failure. Forward checking now will detect a failure, and thus we will backtrack. Although the problem was there before that. I think since we were here or here, I don't remember exactly, but I think since we were here, since we were here, because that was only green. But forward checking did not detect that. So it will backtrack. Let's see now. I will run it, and you will see that it will struggle a lot with this problem until it finds a way around it. Okay, so still here the problem is there, still there. All of that is backtracking, trying to get around this problem. Still there is a problem, as you see, and still a problem. Okay, now it's solved, and it found eventually a solution, but it took a lot of time. Although, as you will see, the situation will be different with arc consistency. But forward checking, it goes into the future, but it doesn't go deep enough into the future to find something like this problem. Now let's switch to our consistency and see on the same exact problem what will happen. So we'll start with assigning this one to blue. Okay, now of course blue is gone from here and there, but also if there is any inconsistency, it will affect the other ones. It seems like there's no problem with the other arcs so far, but now once we assign this to blue, this to red, you will see that this became green, and green is gone from here. And if we go back one step, you will see that green was here. Okay, but now once we assign this one to red, green will be gone from here, and because our consistency go and check all the arcs, green also will be gone from here. Okay, so when we assign this to blue, there's no green here and there is a green here. So this problem is gone from the root. The problem that was very problematic with forward checking is gone forever now for our consistency, much easier and much earlier than before. Okay, now if we continue, I will just run it and you will see that it will go easily. Now when we assign this to blue, the blue has gone from here and now we have red, and red is consistent with this green, so we will not have the problem that we had before. So I will just run it now for forever, and we'll see that there will be no problem, or it will detect that it will not fail into or face that problem. It might do some backtracking in the future, but it will be very small one, and it will find a solution eventually. So you see that it's going very smoothly. There's no backtracking at all. Here there is one backtrack, but it was very quick and it found a way to a solution. Much easier, much faster than forward checking. Okay, any question about these demos? Okay, Saad, third time. Yes, of course. Yes, we said that. Yes, exactly. That is more efficient overall in terms of time. No, it's not only the solution. Maybe they will find the same solution, but doing it's yeah, think about it this way. You might do more work now to avoid doing more work later, which is what our consistency is doing. Yeah, don't think about one situation here and one situation there. Yes, in one point in time, our consistency is doing much more work than forward checking. But forward checking will struggle much in the future, while our consistency will not. So overall, our consistency will be faster. Generally, of course. It's not guaranteed, but generally it will be faster. It will be faster because it looks into the future much more than forward checking. So it might detect failures earlier and thus avoid backtracking. Okay, now coming to the question, I think, Saad, you were the one who asked about the efficiency of backtracking last time, and I told you that we will cover it. We didn't have time last time to cover it. Here is the time. This is for our consistency. Remember, for backtracking in particular, backtracking is depth first search. Okay, so it has the same. If we don't do any improvements, it has the same runtime time complexity like DFS. But now we will talk about the complexity of our consistency. Now, if you look at the pseudocode of our consistency, remember we want to check all the edges. How many edges we need to check? We have n variables, so it's order of n square edges. So that's why we have n square here. Okay, so we'll go through all the ages, and the number of ages is order of n square. Now for each age, what do we do? For each arc, what do we do? This is what we have here, right? What we do is to check all the values in the domain of the tail with all the values in the domain of the head. How many values do we have in the domain of the tail, and how many values we have in the domain of the head? That will be order of d square. We have order of d here and order of d here. D is the number of values in the domain, so it's order of d square. So for every age, we are doing d square computations. Now that's not the only thing that we are doing. We are also adding to the queue if we remove a value from the domain, we are adding more ages to the queue. Now, how many times we do that? I think Saad answered this earlier. We said that we can do that d times only, because we have only d values. Whenever we remove a value, we can add arcs, but we can do that only d times. Okay, only d times. So that's why we have another d here. So we have eventually we have n square d cube runtime or time complexity. It can be reduced to n square d square with some efficiency tricks. We'll not discuss that here, but the original algorithm runs in order of n square d cube. N square because we have the n square edges, d square, the first d square because we are checking values here and there in the tail and in the head, and the other d is because we can remove up to d values from each of the edges, and thus we add arcs. So that's the runtime for arc consistency. With that, we are done with filtering. And remember, filtering was the first step in the three steps that, or the three ways of improvement that we can do over backtracking. Filtering, ordering, structure, and in filtering we discussed forward checking and we discussed arc consistency. Can we do both, by the way, forward checking and arc consistency? Or just one of them? Any ideas? Abdurrahman? It's not just one step, it does that for all the arcs. Yeah. Yes. So there's no point in doing both, of course. It's either you do forward checking or arc consistency. Okay, now let's talk about ordering. And what do we mean by ordering? Remember, in the backtracking search, I told you that there are two choice points. The choice point where we choose which variable we assign next, and there's another choice point where we choose which value we will assign next to that variable. Okay, so there are two decisions here, and so far we just fixed that order. We had a specific order of variables, as you saw in the demo. For example, we go from right to left, and then from bottom to up, and the values were blue, red, green. So we had a fixed order. Now we want to see, can we do better? Can we choose the order of the variables and the values in a way that can make our algorithm or can make finding a solution faster? So that's the topic now that we will discuss. The first one that we will discuss is how to select the next variable to assign. The criteria that we will discuss here is called minimum remaining values. Minimum remaining values, which means that we should select the variable that has the least number or the fewest number of remaining values. Choose the variable with the fewest legal left values in its domain. What does that mean? Let's see an example here. the map is empty, so we can choose any variable because all of them have the same number of possible values in their domain, which is 3 in our map coloring problem. So we can choose any one. Let's say that we choose that one, and let's say that we assign red to it. Now, which variable we should select next? This criteria tells us that we should select the variable that has the minimum number of remaining values. Let's see what are the number of remaining values for each. What is the number of remaining values here? Just 2, right? Because we cannot assign red. Here, it's also 2. Here, it's 3. Here, it's 3. Here, it's 3. Here, it's 3. Okay? Assuming that we are just doing backtracking. Okay? Or forward checking only. If we do that, then the next variable that we should select is one of these two. They have the same number of minimum of remaining values, and they are minimum across over all unassigned variables. So we should select one of these two. Now let's say that we selected this one and we assigned it green. What is the next variable that we should select based on this criteria? Of course, will be that one, because this one has only one remaining possible value, which is blue. This one has 2, this one has 3, this one has 3, and so on. So the next one that we should select is this variable, and then we assign a value to it, which will be blue, of course, here in this case, because that's the only one that is left, and so on. Okay, so that's the criteria. Minimum remaining values. We should select the variable that has minimum remaining value. Now the question is, why minimum, not maximum? Why don't we select the variable that has the maximum number of remaining values, not the minimum number of remaining values? Okay, Ghanem, please stop doing this, please. Sorry. Okay, Abdurrahman. I didn't get your idea exactly, Abdurrahman. So can you say it again? Yes. More troubles. Why? Do you think really we have more troubles? Why? It's the. Go ahead. That's if we choose minimum or maximum. If we choose maximum, we are increasing. Say it again. We are increasing the probability. Actually, it's the opposite, Abdurrahman. If you choose the type, let me explain. If you choose the maximum, then it's the more relaxing one, so it's more flexible, right? So probably you will not remove probably you will not find a problem with that because it has many values, right? But if you choose, so now you are decreasing the value of having a problem. But if you choose the variable that has the least number of values, then this is a problematic variable, right? Because it has only maybe, let's take an example of extreme example that has only one value. If I choose that value, that variable, this variable is problematic, right? Because it only has one choice, and that choice might lead us to a problem soon, because it just has one value. Okay, so that means that if I choose the one with the minimum, I'm actually increasing the probability that I will have a problem very soon. Okay, it's not the other one. I am now increasing the probability that I will have a problem. So that means that it's like I'm looking for problems now. conditions, you mean, we will eventually. Now, we will eventually. Now, remember that we have to assign a value to all variables, Abdurrahman, right? So we have to go through all the variables anyway. But now we are thinking which one we should choose first. Okay? So the criteria here is saying that you should choose first the one that is more problematic. Now the question is why we should choose the one that is more problematic. The answer is choosing the one that is more problematic might or will have the chance of failure very soon. And that's exactly what we want to do. We want to fail much sooner than later. Okay, we would like to fail now so that we can do backtrack now better than having the problem and doing backtracking very late in the future. Okay, please raise your hand if you have any question, and I will call you. Okay, just let me continue this. Let me complete this, and then I will take questions. So let me repeat that again. If you select the variable with the minimum remaining values, then you are selecting the most problematic one, which means that has the chance more to create a problem, to have a failure very soon. And that's exactly what we want. We want to fail. We want to detect failures sooner so that we can backtrack and solve the problem rather than waiting to the future and backtrack because of the problem that we would have discovered much earlier. Mahmoud. Later, after spending more time. So that's exactly why we are selecting the minimum one now, so that we can do backtrack much earlier. Is that clear, Mahmoud? Okay. Ghanem, do you still have a question? Okay. Okay. So you are okay with that now? Okay. Thank you. Type. So this is like here the diagram is really funny. It's like choosing the road that is more scary. We have the ghosts here, than going to the road that maybe has no problem. And the reason here is that you actually want to detect failures as early as possible. So this is called most constrained variable or fail fast ordering. These are the same. These are names of the same criteria. Now we switch to ordering of values. Let's assume now that we selected a variable to be assigned. Now which value we should assign to that specific variable. This criteria is telling us that we should select the value that is least constraining. Least constraining. What do you mean by least constraining? The value that will remove the fewest number of values in the remaining unassigned variables. In other words, the value that is least problematic. That is least problematic because when we assign that value, we didn't remove many other variables, many other values in the neighboring or the remaining variables. So it doesn't make problems more. Type. This is kind of the opposite of the idea of the previous ordering, right? There we said that we should select the variable that is more problematic so that we can detect failures early. Now we are saying select the value that is least problematic so that we don't have problems early. Are these contradicting? Is there a problem with this logic? The answer is no, and I will tell you why. Let me ask you a question before I tell you why. In the selection of variables, are we required to select or to assign a value to every variable or not? Of course, we are required to assign a value to every variable. So we'll have to go over every variable eventually. So it's better to start with variables that are problematic, so that we can detect failures early. But that's not the case with values. With values, we don't have to go through all the possible values. Remember that we target a solution. Okay, so eventually we might not need to try all values. We have to try all variables. We have to assign a value to every variable, but we don't have to go over all values. So it's better, because we want to get a solution, it's better to try values that are less problematic now, so that we don't have problems in the future. So it's not about, we are not here constrained that we will have to try all values. We might have a value, we might assign a value here that will lead me to a solution. But that was not the case with variables. With variables, we know that this variable is problematic anyway. Now or later, it will stay problematic. So it's better to detect it or handle it earlier. But here, we don't have this requirement. Some values will be problematic. Okay, let's avoid them in the beginning, because we might not need to go to them or to try them. Okay, that's why they look contradicting, but actually they are not. So the criteria for the variables is to select the one that has minimum remaining values, and remember always that you want to select the variable that is the hardest, okay, or the most problematic. Here you want to select the value that is least constraining, or in other words, least problematic. Okay, so we should select here least, not the most. And it's the opposite now, that we want to take the road that is easier than the road that is scary. Let me take questions here. Mahmoud. Misal. Actually, we have an example here on the slide. Okay, now let's say that we have these two variables already assigned, and we want to select a value for that variable. Okay, let's say that we selected, we made a decision that this is the variable that we need to assign now. Which value we should select for that variable? We cannot select, of course, green. We only have blue or red. So we have only two choices, blue or red. Now we have to choose one of them. How can we choose one of them? For each value, we see how many values in the domains of the unassigned variables were crossed out, were removed, because we assigned a value here. Of course, this is in simulation. Okay, so we have to do some computations here. Okay, so let's say that this one will and we have to repeat that for every variable, for every value. Okay, so we'll repeat that for red. Let's say that for red, we found that we need to remove 2 values. And for green, we need to remove 4 values from the from the unassigned variables. So now this one is less problematic than this one, because if we choose this one, we have more options. We have more options remaining in our solution. So in that case, we will select this one because it has less number of removals of other values. Is that clear now, Mahmoud? Can you speak in English, because some of the students don't speak Arabic. The one between red and green, this one, yani? But yeah, okay. Just in this example, we assume that we selected this one already, for some reason. Okay, for some reason we selected this one already. Okay, so this is just an example. So we selected that one already, and we need to select now the value for it. Okay, so the criteria says that you should select the value that is less problematic, that will lead to removal of less number of values, so that it will give you more options in the future. And you might not need to maybe backtrack, or you will backtrack less, okay, because you have more options, so it's more flexible. Okay, I hope that it's more clear now. Okay, Saad, you had a question? Quick question, please, because we ran out of time already. Okay, good. One more thing before we leave. Please, by default, consider that we will have a quiz every 2 weeks. So we had a quiz on Sunday in the third week. So we'll have a quiz on Sunday of the 5th week, which means that next lecture we will have a quiz. And inshallah, we will have a quiz every 2 weeks, every Sunday, bi-weekly. Okay, so next Sunday and then 2 weeks after and so on. So the second quiz will be on Sunday, inshallah, and it will cover up to this session. Okay, which is I think 3B. Okay, talk to you inshallah on Sunday, and we'll have the quiz. Assalamu alaikum wa rahmatullahi wa barakatuh.